There's a specific kind of quiet that happens just before sleep. Not sounds exactly, more like the world losing its edges. Sounds are still there, the hum of something mechanical in another room. Maybe rain, maybe not, maybe just the building settling into itself the way old things do. And your attention, which spent all day sharp and directed and useful, starts doing something softer, starts drifting toward things that don't require anything back. That's what this is for. This project, the Sleepy Physicist, runs without sponsors, without a brand deal, without anyone's logo at the beginning or end of anything. It's self-funded, which is a polite way of saying it exists because people like you decide it's worth keeping alive. If that's something you want to be part of, Patreon is where that happens. And, this feels worth mentioning, somewhere around 200 members we're going to open a Discord. A proper one. A place for people who lie awake thinking about dead stars and collapsing matter and the strange edges of what physics allows. Curious people finding each other. That's the idea. If that sounds like your kind of room, you know where to go. For now, though, just this. There's a star that isn't a star anymore. And before anything else can be said about it, before the cracking or the fractures or the violence of what it does, the thing itself has to be understood. Or not understood exactly. Felt, maybe. Held in the mind long enough to stop being a number and start being something real. Here's where most explanations start badly. They open with mass. They say 1.4 solar masses, and let that sit there like it means something to a person lying in bed in the dark. It doesn't. Not immediately. Solar masses are a unit humans invented to measure things they cannot physically approach, and they arrive in the brain as data rather than weight. So set that aside for a moment. Think about a city instead. Not a metaphor, an actual measurement. The object we're describing is roughly the size of a city, London, Chicago, the kind of place that takes 40 minutes to drive across at a reasonable speed, the kind that has neighbourhoods and rivers and districts and all the complicated horizontal sprawl that human settlement produces over centuries. That physical footprint, that diameter, 20 kilometres, give or take. That's the size of what's left when a star several times larger than our sun finishes burning, collapses and then stops, not because it ran out of energy to collapse further, but because the stuff it's made of physically refuses to be compressed any smaller. Inside that city-sized space sits more mass than our entire sun. Take a second with that. Not the number, the shape of it. Our sun is enormous in a way that resists easy description. It is 1,000,000 Earths. It is a thing so large that the Earth's entire orbit fits comfortably inside it, and a neutron star, this city, holds that much mass, or more, in a sphere you could drive across in the time it takes to watch a film. The density that results from this is not a number that translates easily. 1 teaspoon, one small ordinary kitchen teaspoon of the material this star is made of would weigh, and this is not exaggeration, this is the physics, somewhere around 1 billion tons, or 4 billion depending on which estimate you trust, depending on exactly where in the star you're scooping. The number shifts a little in the literature, but the order of magnitude doesn't. It's always billions. It's always that category of weight, applied to a volume you could hold in your hand. There's a wool blanket kind of heaviness to thinking about that. A settling, like something pressing down. The surface gravity of this object is roughly 200 billion times the gravity you feel right now, which means that if you were somehow standing on its surface, and you wouldn't be, but follow the thought anyway, the gravitational pull would be so extreme that the act of falling, which on Earth is a gentle and recoverable experience, becomes something else entirely. Not dangerous in the way heights are dangerous. Dangerous in the way that physics stops cooperating with the idea of a human body. Light itself has to work to leave this object. That's not a figure of speech. Light, which has no mass, which travels as fast as anything in the universe is permitted to travel, has to spend energy climbing out of the gravitational well of a neutron star. It redshifts. It slows at the surface fractionally, in ways that become measurable. The object bends space-time around itself so aggressively that what happens on one side of the star is gravitationally lensed to the other side, meaning a telescope pointed at a neutron star can, in principle, observe more than half of its surface at once. The far side wraps around. The geometry of behind doesn't quite work the same way here. And this, all of this, the impossible mass, the warped light, the weight beyond weight, this is the stable state, this is the object at rest. What it does when it isn't at rest is what this is all building toward. But not yet, because the surface needs to be understood first, or not the surface exactly, the stuff the surface is made of, which is not rock or metal in any sense those words have ever meant before. The outer crust of a neutron star is, technically, a solid. A rigid crystalline lattice of atomic nuclei, mostly iron, or iron-like nuclei, packed so tightly and held in place by pressures so extreme that the lattice is somewhere between 10 and 100,000 times stronger than steel. Not the thickness of a steel plate, the material itself, the crystalline structure, its resistance to deformation. Call it the strongest solid anything has ever formed, because as far as anyone can verify, it is. Deeper than that, the nuclei start doing something stranger. The pressure increases past the point where individual nuclei can hold their shape cleanly, and they begin to elongate, to merge, to sheet into flat planes and then curl into tubes. Physicists name these structures after pasta, and yes, that is the actual terminology used in peer-reviewed astrophysics literature. And no, there isn't a better word for it. Spaghetti. Lasagna. Bucatini. The shapes appear at densities no laboratory on Earth has ever produced, and they were predicted by equations long before anyone could observe them directly. This is the inner crust, where matter, under enough pressure, gets structurally creative in ways that human experience has no vocabulary for except borrowed from the kitchen. Below that is the core, which is where certainty frays. At the densities found in the interior of a neutron star, the behavior of matter is genuinely unknown. Not unknown in the "we haven't studied it enough" sense, unknown in the "no experiment we can currently run reaches these conditions" sense. The equations offer several possibilities. Maybe pure neutron fluid, maybe something stranger, hyperons, which are particles that don't survive long enough in normal conditions to study carefully. Maybe quark matter in which the quarks that normally huddle inside protons and neutrons have broken free and formed their own continuous fluid. Maybe something that has no name yet because no one has had to name it. It seems, and this is genuinely uncertain, which is a strange thing to sit with, it seems like we are describing the interior of a common object. There are hundreds of millions of neutron stars in the Milky Way alone. This bizarre, pasta-crusted, quark-maybe fluid thing is not rare. It is ordinary. It is a standard outcome of stellar death, scattered across the galaxy like the ruins of old fires. The city metaphor keeps coming back. A city made of collapsed fire, something that used to be enormous and radiant, now compressed into an object a person could theoretically jog across the diameter of in a few hours. If jogs were survivable in this context, which they are not. But the scale is approximately right. 20 kilometers, a city, full of matter in states that have no parallel anywhere else. And it spins. That part comes next, but already, even before the spinning, even before the crust begins to feel the first hint of stress, The object is extraordinary in a way that has nothing to do with what it's about to do, just sitting there, just existing, already the most structurally strange thing in the observable universe. The cracking hasn't started yet. But the crust is not entirely at peace either. Press your thumb into a wooden table. Not hard enough to hurt, just hard enough to feel the resistance. The grain pushes back. The wood doesn't flex, doesn't accommodate, doesn't negotiate. It simply holds its shape against you with a kind of stubborn structural indifference. That refusal is what solidity feels like from the outside. Now imagine a material that makes that table feel like fog. The outer crust of a neutron star is the strongest solid anything in the observable universe has ever produced. Not the thickest, not the most massive, the strongest in terms of what it takes to deform it. Its breaking strain, the technical measure of how much stress a material absorbs before it fails, is somewhere around 10 billion times greater than steel. Not times. 10 billion. The number is almost inconvenient. It sits in the research papers with a kind of quiet confidence, and if you stare at it long enough, it stops feeling like a measurement and starts feeling like a boundary marker. Beyond this point, the word strong no longer applies. A new category is needed. The crust is roughly 1 kilometre thick, which sounds thin given the object it belongs to, a skin over a city more or less. But that kilometre is doing an extraordinary amount of structural work. It is the outermost layer of a system under gravitational compression so extreme that every cubic centimetre of its material is being squeezed from all directions simultaneously, not by external force but by the sheer weight of the object pressing inward on itself. The crust doesn't hold the star together. The star's gravity holds the crust in. There's a difference in those two directions that matters. At the very surface, the top of the crust, if top means anything on a spherical object with no atmosphere to orient you, the material is iron, or what used to be iron more or less. Fully ionized nuclei stripped clean of electrons arranged into a rigid body-centered cubic lattice. A crystalline structure technically, though the word crystal usually brings to mind something transparent and delicate found in rock shops, and this is neither of those things. This crystal would make diamond look structurally timid. The electrons that were stripped from those nuclei aren't gone. They form a surrounding gas, dense, degenerate, quantum mechanically strange, flowing between the nuclei holding the whole lattice electrically neutral. The whole system is balanced in this precise and pressurized way, and it is, by all the measures physics uses for such things, a solid. It behaves like one. It has rigidity, it has shear modulus. It has all the mechanical properties of a material that will resist being bent or broken. It just happens to be held together by conditions that no laboratory on Earth can replicate. Deeper. A few 100 meters down, the pressure climbs. The iron nuclei can't stay iron. The electrons are being forced into them, converting protons to neutrons through a process called electron capture, and so the nuclei become progressively more neutron-rich as you descend. Unstable by any earthly standard, but stable here because the dense electron gas suppresses the decay that would otherwise happen instantly. The matter is being held in a state it would never voluntarily occupy. It's not comfortable. If comfort is a word that can be extended this far, it simply has no choice. Around 400 grams per cubic centimetre. Actually, no, that's the wrong unit entirely. The densities here are measured in grams per cubic centimetre, but the numbers reach into the hundreds of millions. So ordinary density intuition collapses somewhere around here. The nuclei start to leak. Neutrons begin to drip out of the nuclear clusters and move freely through the surrounding space. This is called, with admirable plainness, the neutron drip point. and it marks the transition from the outer crust to the inner crust. The outer crust held its nuclei intact. Even if it modified them, the inner crust lets them bleed. This is where things get structurally strange. The inner crust is not a single material with a single geometry. It is a zone where the shape of nuclear matter is actively negotiating with pressure, and the negotiations produce different outcomes at different depths. At the upper end of the inner crust, you still have nuclei, bloated, neutron-heavy, not quite the iron of the surface but recognizably nuclear clusters, sitting in a sea of free neutrons. Descend further and the clusters start to lose their spherical shape. They elongate, they become rods, push deeper still and the rods merge into sheets, then the sheets develop holes, then the geometry inverts entirely and what were once solid clusters become cylindrical tunnels through a continuous nuclear fluid. Physicists call this the nuclear pasta phase, which is the correct term, used without embarrassment in serious astrophysics literature, because there genuinely wasn't a better vocabulary available when these structures were first predicted. The shapes map almost perfectly. Spherical clusters are gnocchi, rods are spaghetti, sheets are lasagna, the inverted cylinders are anti-spaghetti or bucatini depending on who you're reading. The naming is not whimsical, it is actually descriptive, which is somehow more surprising than if it had been a joke. These structures exist because matter under extreme pressure finds the lowest energy configuration available to it, and at these densities, flat sheets and hollow tubes are more stable than ordinary spheres. The geometry is determined by the balance between nuclear surface tension, which wants to minimize contact area, and the Coulomb repulsion between protons, which wants to push charges apart. In between those two forces, in the specific conditions found in the inner crust of a neutron star, you get pasta, kilometers of it, layered through the deepest part of the solid shell, forming the structural foundation of the object that will, eventually, fracture. The pasta phase is, by the estimates available, harder to break than the iron lattice above it. Molecular dynamic simulations, which model the behavior of these structures by tracking the interactions of the individual particles across enormous numbers of time steps, suggest the breaking strain in the pasta region exceeds even the already extraordinary values of the outer crust. The material grows stranger and stronger simultaneously as depth increases. This is not always how things work. Usually under enough pressure, materials weaken and flow. Here the pressure is doing the opposite. It is manufacturing rigidity. And inside all of this, threaded through the inner crust like a second substance entirely, are free neutrons in a superfluid state, not individual particles moving around. A superfluid, matter that has transitioned into a collective quantum state where viscosity disappears and flow becomes frictionless, and rotation produces quantized vortices instead of the ordinary swirling of classical fluids. The free neutrons in the inner crust, at the temperatures and densities found here, have paired up in a way that allows them to behave collectively rather than individually. The crust is rigid. The superfluid flowing through it is not. They coexist in the same space, occupying the gaps between nuclear structures, one solid and one frictionless, one locked in a lattice and one drifting freely through it. The implications of that coexistence are significant. Or, more carefully, one specific implication of that coexistence is what this chapter is slowly approaching. But not yet. For now, just this. The crust is not a simple thing. It is not one material. It is a sequence of different phases of matter, each responding to increasing pressure by becoming something new, each stranger than the one above it, each harder, each more structurally foreign to anything human hands have touched or human experiments have produced in a laboratory setting. 1 kilometer of the most exotic solid the universe has assembled, sitting on the surface of a 20-kilometre object, surrounding a core whose behaviour is genuinely unknown, spinning in the dark at rates that no solid object of this size should be able to sustain without flying apart. But it doesn't fly apart. That's the thing. Despite the rotation, and the rotation is fast, sometimes unimaginably fast, though that comes later, the crust holds. The gravity pressing inward is, for the moment, more insistent than the centrifugal tendency to expand outward, and so the lattice stays intact, the pasta stays layered, the superfluid threads quietly through the rigid structure above the liquid core, and everything is, for now, held. The surface doesn't look like ground. There's no way to describe what it would look like exactly because no instrument has imaged a neutron star surface directly, and probably none will for a very long time. It radiates X-rays. It has a magnetic field of inconceivable strength locked into its structure. It is almost certainly perfectly smooth, smoother than any manufactured surface on Earth, because the gravity is strong enough to flatten any feature taller than a few centimeters. A mountain on a neutron star is a few centimeters high. That is not a poetic exaggeration. That is what the math produces when you apply neutron star gravity to the question of how tall a geological structure can stand before being crushed into the crust by its own weight. Flat, rigid, crystalline, magnetic, and about to endure something it was not designed to endure gracefully. There is a slow process beginning, has already been beginning for thousands of years before any of this story starts, that will put the crust under a different kind of stress. Not the compression of gravity pressing inward. Something more subtle, something built from the star's own motion, working against the material's insistence on keeping its shape. The crust wants to stay the way it is. The physics will disagree. It is born fast, not fast the way a thrown object is fast, or fast the way wind moves across flat ground. Fast the way physics becomes reckless when enormous mass collapses into a tiny space, and conservation of momentum has nowhere to put itself except into rotation. The original star, the one that died to make this object, was rotating slowly the way most stars do, taking weeks or months to complete a single turn. Then its core collapsed. In seconds, something the size of the sun, compressed to something the size of a city, and all that rotational momentum which belonged to an enormous slow sphere now belonged to a tiny dense one. The spin rate didn't decrease with the radius. It exploded. Newly born neutron stars rotate hundreds of times per second, not once per second, not 10 times, hundreds. In the time it takes to read this sentence aloud, a newborn pulsar completes more rotations than the Earth completes in an entire day. The equatorial surface, the widest part, is moving at a significant fraction of the speed of light, and this is the normal outcome of stellar collapse, not an anomaly, the standard product. At that speed the star bulges at its equator. Has to. The centrifugal tendency, the outward push of rotation, is strong enough to deform even this material, strong enough to overcome partially the gravity pressing inward, and so the star is not quite a sphere. It is an oblate spheroid, wider at the middle than at the poles. The crust, which forms early and forms rigid, freezes into this slightly flattened shape. The lattice crystallizes around the equatorial bulge. The pasta layers set, the structure locks, and then the star begins to slow. This is not a dramatic process. There is no friction, no atmosphere to push against, no drag in the ordinary sense. What bleeds the spin away is electromagnetic radiation. The pulsar's magnetic field, which is enormous and rotating with the star, sweeps through space and generates radiation, and that radiation carries energy away, and that energy comes from the rotation, and so the rotation decreases, slowly, measurably, but slowly. A pulsar might lose a few microseconds from its period over the course of a year. Some lose less. Some, the youngest and most energetic, lose more, but the direction is always the same, always towards stillness, across timescales that don't fit easily inside a human sense of duration. Thousands of years, tens of thousands. Some pulsars are old enough that they have been slowing since before recorded human history began, before agriculture, before anything on this planet that could be called civilization had assembled itself into a form we'd recognize. They were already spinning when the first cities were built. They were already slowing. They are still slowing now, tonight, while you are horizontal in the dark, while the room around you is quiet, while your own breathing has started to deepen in the particular way it does when consciousness begins to soften at its edges. The spin decreases. The equatorial bulge should decrease with it. A sphere rotating more slowly has less centrifugal force pushing outward at its equator, which means gravity can pull the equator in slightly, which means the shape should become slightly less flat, slightly more spherical. This is what the physics wants. This is the equilibrium shape at any given rotation speed, and as the speed decreases, the equilibrium shape changes, and the object should follow it. The crust does not follow it. This is the problem, or not the problem exactly, more like the condition that makes everything else possible. The crust is too rigid to simply comply with what the new equilibrium demands. When the star was spinning at birth, the crust formed around that shape, the lattice locked in, the crystalline structure set with that oblateness built into it. And now, thousands of years later, the star is spinning slower, and the equilibrium shape is less oblate, and the physics is quietly, persistently applying stress to the crust in the direction of the new shape, trying to pull it inward, trying to make the equator shrink. And the crust is passive, resisting, not actively, not with any agency. It resists the way any sufficiently rigid material resists deformation. By storing the energy of that deformation internally in the bonds between particles, in the geometry of the lattice, distributing the stress through its structure rather than yielding to it. This is what solids do under loads they cannot yet break. They absorb, they accumulate, they hold. There's a specific kind of tension that lives in a body that has been holding something for too long. You might know it from your own shoulders, the kind of tightness that isn't painful exactly, but that you only notice when someone mentions it, or when you finally let go of it and feel the difference. Held tension, structural tension, the body maintaining a position it was originally placed in long after the reason for that position has passed, because relaxation requires a different kind of effort than holding ever did. The crust is doing this, across centuries, across millennia. The star it belongs to is no longer spinning fast enough to justify the shape the crust was born with, and the physics is applying a persistent, gentle, irresistible load in the direction of correction. And the crust is holding, storing every bit of that unrelieved stress in the geometry of its lattice, in the angles between nuclear clusters, in the microscopic deformations of a material that has not yet reached its breaking point but is incrementally approaching it. The stress accumulates the way certain kinds of debt accumulate, not the kind you notice month to month, the kind that was decided years ago by conditions that no longer exist, whose consequences arrive later, all at once, in a form that seems sudden but wasn't. No alarm announces this, no signal propagates outward. To any telescope watching this pulsar, and there are telescopes watching, tracking its pulse like a slow and incredibly precise clock, the star appears stable, regular. It is flashing its radio beam across the galaxy with a consistency that loses less than a millisecond per year. Nothing in that signal says the crust is under load. Nothing in the timing says something is building. The interior knows, in a physical sense, the stress exists, is real, is measurable in principle, even if not in practice from this distance. But the exterior broadcasts nothing except the steady, slightly slowing pulse of a dead star doing what dead stars do, which is almost nothing for a very long time, and then something else. There is something happening inside the crust that the crust does not know about. Or, that's not quite right, physically. The crust knows in the sense that matter always responds to adjacent matter. But the interaction is weak, deliberately, structurally weak. What lives inside the rigid lattice and the pasta layers and the stacked crystalline geometry of the outer shell is a substance so fundamentally different in its behavior that it might as well be a different kind of physics altogether. It flows through the gaps in the crust the way something with no viscosity flows, which is to say without resistance, without slowing, without any of the normal mechanical negotiation that fluids and solids conduct when they are pressed together. This is the neutron's superfluid, and it is deeply, quietly strange. Start with temperature, because temperature is where the strangeness begins. Neutron stars are hot by most standards. The interior temperature sits somewhere around 100 million Kelvin, which is an almost absurd number, the kind of temperature that exists briefly in nuclear reactions and persistently in the interiors of stars, not in dead objects drifting through the dark between other stars. 100 million Kelvin sounds like the opposite of a superfluid. Superfluids, in every laboratory context ever encountered on Earth, exist at temperatures near absolute zero. Helium, cooled to within a degree or two of the coldest possible temperature, transitions into a frictionless state. Liquid nitrogen isn't even close to cold enough. It has to be within a whisper of zero. And yet, the neutrons in the inner crust of a neutron star are superfluid at 100 million Kelvin. Not because the temperature isn't extreme, but because the density is more extreme than the temperature. At the pressures found inside this object, the neutrons pair up, a quantum mechanical pairing mediated by the nuclear force that creates what are called Cooper pairs, named for a physicist who worked out the mathematics of this kind of pairing in the context of electrons in superconductors, long before anyone applied it to neutron stars. These pairs behave differently from individual particles. They fall into a collective quantum state, all sharing the same wave function, all moving in a coordinated way that eliminates the ordinary scatter and friction of particle interactions. The temperature that would normally destroy this state is simply overwhelmed by the density that creates it. The result is a fluid that does not slow down when it moves, does not dissipate, does not transfer its energy to its surroundings through friction. It flows and it keeps flowing, and the only way to change its rotation is through specific, quantized, physically constrained mechanisms that have nothing to do with ordinary viscosity. One of those mechanisms involves vortices. When a superfluid rotates, and it does rotate, was rotating when it formed, and has been rotating since. It cannot rotate the way a normal fluid rotates, where every part of the fluid shares smoothly in the overall spin. A superfluid, because of its quantum nature, can only carry angular momentum in specific quantized units, and it does this by forming discrete rotating structures called vortex lines. Thin tubes, each one carrying exactly one quantum of angular momentum, arranged throughout the superfluid in a regular array. The more vortices, the faster the overall rotation. The fewer vortices, the slower. To spin down, the superfluid must eliminate vortices, must push them outward to the boundary, where they can dissipate. In a laboratory superfluid, this happens smoothly. The vortices migrate, the spin decreases, everything cooperates. In a neutron star, the vortices are pinned. This is the part that changes everything, and it is, when you sit with it, a genuinely strange situation to imagine. The vortex lines threading through the neutron superfluid are pinned to the nuclear clusters in the inner crust. Pinned in a physical sense, the energy configuration is such that a vortex sitting against a nuclear cluster is in a lower energy state than a vortex moving freely, and so the vortices lock themselves to the lattice, to the pasta structures, to the rigid crystalline material surrounding the superfluid, like bristles caught in a grate. They cannot simply migrate outward. They are held in place by the geometry of the crust. So when the crust slows, when the electromagnetic radiation bleeds rotational energy away from the outer shell of the star, and the rigid lattice decelerates, carrying the magnetic field and the radio beam with it, the superfluid does not slow with it. Cannot. Its vortices are pinned to the crust, yes, but the mechanism by which they would reduce their number, by which they would migrate and dissipate and allow the superfluid to lose angular momentum, is suppressed. The crust slows. The superfluid essentially does not. There is a gap that opens between them, not a physical gap. They are still occupying the same space, the superfluid still threading through the pores of the inner crust lattice, still present in the same cubic kilometre of star, but a rotational gap, a velocity difference. The crust is spinning at one rate, the superfluid at another, and the difference between those rates is growing imperceptibly, persistently, as year follows year and century follows century, and the crust continues to decelerate while the interior holds its speed. There is something, and this is a strange comparison to reach for, but it keeps arriving. There is something about lying completely still in bed, at the end of a long day, while the mind is still moving. The body has stopped. The body is horizontal, relaxed, not going anywhere. But something inside hasn't gotten the message yet. Still turning over something that happened hours ago, still carrying velocity that the rest of the system has shed. That gap between the body's stillness and the mind's ongoing motion. The crust and the superfluid are doing something structurally similar, except the gap is real, is physical, is measured in differential rotation rates and stored in the geometry of vortex arrangements across the entire interior volume of a star. The vortices, pinned to the crust but embedded in a superfluid that is spinning faster than the crust, experience a force, the Magnus force, a hydrodynamic lift, the same family of physics that makes a spinning baseball curve applied here to the quantized vortex tubes in a neutron superfluid. The faster the lag grows between the crust and the superfluid, the stronger this force becomes, pushing the vortices outward, trying to drive them toward the crust core boundary, where they could dissipate and allow the superfluid to spin down to match the crust. But the pinning resists. The vortices are held. The force builds against the pinning energy, and the pinning holds, and the force continues to build, and the pinning continues to hold, and this tension accumulates the way pressure accumulates in a sealed system, invisibly, without external signal, distributed across an enormous number of individual pinning sites spread throughout the inner crust, each one holding its vortex against an increasing load. From outside, from the perspective of a radio telescope on Earth, tracking this pulsar's timing, none of this is visible. The pulse arrives. It is slightly late compared to last year. Slightly later than that. The spin down is smooth, or appears smooth, or is smooth enough that the small irregularities are lost in the measurement uncertainty. The observatory records another data point. The star appears to be doing nothing except decelerating quietly in the dark. The interior is not doing nothing. There are, at any given moment in the life of mature pulsar, somewhere on the order of 10 to the 18th power of the individual vortex lines distributed through the superfluid, a number so large that it is genuinely difficult to hold as a count of discrete objects rather than as a texture, a density, a quality of the material rather than a list of things, each one pinned, each one under load, each one contributing its fraction to the total stored angular momentum that the superfluid is carrying in excess of the crust. The total excess is not large in absolute terms, not compared to the star's overall angular momentum, not compared to the energies involved in the crust's own rotation. It is a small fraction, a few percent of the crustal moment of inertia, at most sometimes estimated as low as 1 to 2%. This is, in a sense, reassuring. The system is not dramatically out of equilibrium, not poised on some catastrophic edge, except that a few percent of the angular momentum of a neutron star is not a small amount of energy in any human sense, and it is all waiting, pinned in place, held by a force that has a maximum value beyond which it will fail. The crust, meanwhile, is also under stress. The shape stress described in the previous chapter, the mismatch between the crust's frozen oblateness and the equilibrium shape demanded by the current spin rate, is ongoing, adding to the load on the lattice, pressing quietly on a structure that is already holding more than it was designed for. The two stresses are different in origin and different in geometry, but they share a destination, the crust, which must bear both, which has been bearing both, which has no mechanism for gradual relief. What happens when the pinning fails is, well, that's not this chapter. This chapter is just the weather, the internal conditions, the slow accumulation of everything that has to exist before anything can happen, the superfluid spinning ahead of the crust, the vortices pinned and loaded and waiting, the crust holding its shape against a physics that wants a different shape. All of it sealed inside a kilometre of the strongest material in the universe, invisible from outside, unannounced, patient in the way that only physics can be patient, without intention, without anticipation, simply present and accumulating. There is a threshold. Somewhere ahead there is a threshold. Whether it is reached from the inside, the vortex pinning failing under accumulated load, or from the outside, the crustal lattice finally fracturing under shape stress, or from some combination of both, is a question that the literature argues about carefully and without resolution. The honest answer is that the triggering mechanism for pulsar glitches is still not fully settled. What is known is that the threshold exists, and that the system is moving toward it, and that when it is reached, the interior weather that has been building quietly for centuries will find a way out. The crust doesn't know it yet. Or, again, that's not quite the right way to put it. The crust knows in every bond and lattice angle and pinning site. It has been knowing for a long time. It just hasn't broken. It doesn't build to anything. There is no crescendo, no final tremor that announces what's coming. The crust has been under load for centuries, the shape stress accumulating in the lattice, the vortex pinning, straining against the rotational lag, the whole interior system holding its two separate tensions in the same rigid shell. And then, at some specific moment that has no special quality distinguishing it from the moment before, the lattice reaches the end of what it can absorb, and it gives, not gradually, not in the way that metal fatigues slowly, showing cracks that widen over time, giving engineers the chance to notice and intervene. The failure is sudden in a way that the word sudden barely covers. It happens on a timescale measured in milliseconds, possibly microseconds, a rearrangement of crustal geometry so fast that it falls below the threshold of any process that could be called gradual. The crystalline structure that has been holding its stress for 1,000 years releases it in less time than it takes a nerve signal to travel from a fingertip to a brain. One section of the crust slips, the displacement is approximately 1 millimeter, maybe less in some events. The estimates vary depending on the model and the specific glitch being analysed, and the honest position is that no one has directly observed the fracture geometry of a neutron star crust from close range, and no one will for the foreseeable future. What is known comes from the aftermath, from the timing data, from the spin-up, from the quasi-periodic oscillations that follow. Working backwards from those signals, the crustal shift that could produce the observed effects is small. Astonishingly, almost offensively small. 1 millimeter, the thickness of a credit card, the gap between a door and its frame on a humid day. On this object, that is not a small displacement. Here is where the personal opinion has to come out, because the physics here is genuinely unsettling in a way that the neutral voice doesn't fully capture. There is something deeply wrong feeling about a millimeter being catastrophic. The human intuition for scale says that millimeters are the domain of the inconsequential. Small adjustments, fine tolerance, the kind of measurements that matter in watchmaking and surgery, but not in anything cosmic. The neutron star crust doesn't know this. It doesn't have access to human intuitions about scale. It only knows density and gravity and the energy stored in the geometry of matter under extreme compression. A millimeter of displacement in that context moves mass, not a little mass. The crust is 1 kilometer thick and spans the entire surface of a 20-kilometer sphere, and every cubic centimeter of it weighs somewhere in the neighborhood of 100 million tons. When a section of that structure shifts by a millimeter, the energy released by that shift, the gravitational potential energy alone, before the elastic strain energy stored in the lattice is even considered, is measured in units that require scientific notation to write down comfortably. The temperature at the fracture site spikes, immediately locally to values high enough to vaporize, not heat, not melt, vaporize, hundreds of trillions of metric tons of matter. The surface above the fracture radiates this energy outward in the form of X-rays and gamma rays, a burst of high-energy light that propagates away from the star at the speed of light in all directions, carrying the news of the fracture to whatever detectors happen to be oriented toward this part of the sky. The magnetic field convulses. The crust of a neutron star is not just structural, it is the physical anchor of the magnetic field. The field lines are embedded in the lattice coupled to it, locked to the crystalline structure the way. This is the one soft metaphor the chapter will allow. The way iron filings lock to the geometry of a magnet, unable to rearrange without the whole field rearranging with them. When the crust slips, the field moves with it. The geometry of the field changes suddenly on the same millisecond timescale as the fracture. Field lines that were in one configuration are in another configuration, and the energy difference between those two configurations is released into the surrounding magnetosphere as a violent pulse of electromagnetic radiation. The two energy sources, mechanical and magnetic, arrive together. They are not separable in the burst. What a detector registers is their combined output, a spike of gamma rays and X-rays that can, in the case of the most energetic events, be detected across the entire galaxy. The star doesn't pause here. There's something about this moment, the fracture, the spike, the impossible energy from a millimeter of motion that we're going to go much deeper on. On this channel, we're building toward dedicated mini deep dives, shorter, more focused explorations of single concepts like this one. Those launch at 500 members. The link to join is in the description. If this is the kind of thing you want more of, that's where it happens. The fracture propagates. Not infinitely. The crust isn't shattering, isn't disintegrating, isn't being destroyed. It is failing locally, at the site of maximum stress concentration, and the failure travels outward from that point as a shear wave moving through the crystalline structure at speeds comparable to a significant fraction of the speed of sound in neutron star matter, which is fast. Neutron star matter is so dense and so rigid that the speed of sound in it approaches 1/10 of the speed of light, and a shear wave propagating at even a fraction of that through the crust crosses the entire circumference of the star in a time that is, by human standards, essentially instantaneous. The whole crust knows what happened almost immediately. And then, this is the part that takes longer, the part that unfolds over seconds and minutes rather than milliseconds, the interior responds. The vortex lines that were pinned to the inner crust, holding the superfluid's excess angular momentum in place, feel the sudden mechanical disturbance. The pinning sites shift. The geometry that was holding the vortices in place is no longer quite the same geometry, and across an enormous number of pinning sites simultaneously, the vortices unpin. The superfluid releases its stored angular momentum into the crust. Not all of it, a fraction, a few percent at most of the total stored excess. But on a neutron star, a few percent of the stored angular momentum in a superfluid that has been accumulating rotational lag for centuries is enough to do something measurable from the other side of the galaxy. The crust speeds up, a tiny amount, a fraction so small it would be invisible in almost any other context. But this object is a clock, the most precise natural clock in the universe, broadcasting its rotation rate across interstellar space with every pulse of its radio beam, and when that clock suddenly runs fractionally fast, the telescopes watching it notice. That notification is called a glitch, and the glitch is how, from 50,000 light-years away, we know that any of this happened at all. Pick up a coin, any coin, the specific denomination doesn't matter, just the physical object, the weight of it in the palm. It is, depending on the coin, somewhere between 1 and 3 millimeters thick. A small thing, an amount of space that exists to accommodate fine tolerances and minor variations, the kind of measurements that appears in manufacturing specifications and medical dosages, and the gaps that woodworkers care about, and most other people never think about at all. This is the scale of what happened. Not the coin, the thickness. 1 millimeter of displacement in the neutron star crust, 1 millimeter of crustal slip, somewhere along a fault line in the lattice, at a location under pressures and densities that have no earthly parallel. And because this is a chapter about what that millimeter actually means on this particular object, the comparison to the coin has to be set down almost immediately, because the coin is already misleading. A coin's thickness is a gap in air. A millimeter of neutron star crust is a millimeter of matter at densities where the word matter itself starts to feel approximate. Start with the mass involved. The crust is roughly 1 kilometer thick, covering the entire surface of a sphere 20 kilometers across. The surface area of that sphere is approximately 1,200 square kilometers, not enormous by planetary standards, easily dwarfed by a mid-sized country, smaller than the state of Rhode Island. But every square meter of that surface and every cubic meter of depth beneath it is made of material that weighs somewhere in the hundreds of millions of tons per cubic centimeter. A single cubic centimeter, the volume of a small sugar cube, hundreds of millions of tons. When a section of that crust displaces by 1 millimeter, the mass that moves is not a gram, not a kilogram, not a ton. The estimates for the mass involved in a typical starquake-driven glitch are in the range of 10 to the 17th kilograms, which is approximately the mass of a small moon. A small moon, moving 1 millimeter, under a gravitational field 200 billion times stronger than the one currently holding you horizontal in your bed. The gravitational potential energy released by that movement alone, before the elastic strain energy stored in the lattice is included, before the magnetic energy is touched, is approximately 10 to the 40th ergs. That number needs a comparison to land, and the comparison that keeps arriving, the one that is, I'll say it plainly, the most disturbing of all the numbers in this chapter, is the Sun. Our Sun radiates energy, constantly in all directions, from a surface 12,000 kilometers across through nuclear fusion that has been running for 4.5 billion years. The total power output of the Sun, the number that appears in physics textbooks as the solar luminosity, is approximately 3.8 times 10 to the 33rd ergs per second, every second. That is an enormous rate of energy release by any measure available to human intuition. The gravitational energy released in a pulsar starquake exceeds the total energy our Sun will radiate across 100,000 years. Not 100,000 seconds, 100,000 years. A duration longer than anatomically modern humans have existed on this planet, longer than the entirety of recorded history multiplied by roughly 50, released in a fraction of a second by 1 millimeter of movement in a crust the size of a small city. The elastic energy stored in the lattice, the mechanical energy, the spring energy, the energy of a rigid crystalline structure that has been bent slightly out of its preferred geometry for centuries and is now releasing that deformation all at once, adds to this. The estimates for the elastic component vary, but the combined energy budget of a major starquake sits comfortably in the range of 10 to the 44th ergs for the most energetic events, which is, the comparison here almost defeats itself, which is the kind of number where the solar comparison, already staggering, has to be extended further than feels reasonable. Set the solar comparison aside. It has done its work and it doesn't scale cleanly beyond this point. Think instead about what the energy does when it leaves the fracture site. Some of it goes immediately into heat. The temperature at the fracture surface spikes to values that vaporize the surrounding material. Not gently, not gradually, but instantaneously, in a flash that converts solid crust into plasma in a region around the slip surface. The X-rays produced by this spike propagate outward through the magnetosphere and away from the star at the speed of light. If a detector is pointed at this star, it sees a sudden brightening in the X-ray band. The brightening lasts seconds to minutes, depending on the event. Some of the energy goes into mechanical waves, shear waves propagating through the crust at speeds approaching 1/10 of the speed of light in some models, setting the whole star vibrating at frequencies in the range of tens to thousands of hertz, a ringing that is encoded in the oscillating brightness of the burst and can be read backwards to say something about the interior structure of the object. This is called astroseismology, and it is one of the few direct windows into what the inside of a neutron star is actually doing at the moment of a fracture. And then there is the magnetic energy. The magnetic field of a neutron star is not a field that exists around the object the way Earth's magnetic field exists around Earth. Something external generated by internal currents but separable from the material itself. The neutron star's field is embedded in the crust, anchored there. The field lines pass through the crystalline lattice and are locked to it. And when the lattice moves, the field moves, and when the lattice moves suddenly and violently, the field responds in kind. What happens to the magnetic field of a magnetar, a neutron star with a field 1,000 times stronger than an ordinary pulsar, when the crust fractures is something between a reconfiguration and a detonation. The field lines, which were in one geometry, are forced into another geometry, and the difference in magnetic energy between those two geometries is released. Not slowly, not gradually. In the same millisecond timescale as the mechanical fracture, magnetic energy converts to radiation, gamma rays primarily, but also electrons and positrons born from the energy itself, matter and antimatter, produced directly from the electromagnetic energy of a rearranged field, those electrons and positrons meet and annihilate. Their annihilation produces more gamma rays. The magnetosphere surrounding the star, which was moments ago a structured region of field lines and charged particles in some approximate equilibrium, is now a fireball expanding outward at a significant fraction of the speed of light. For approximately 1/10 of a second, this object, which was a slow-dying dead star, which was decreasing in brightness over geological timescales, which was doing nothing that would cause any particular alarm, becomes briefly brighter than anything else in the galaxy, brighter than the combined light of 100 billion stars, from 1 millimeter. That is what density does to scale. That is what it means to have the mass of a star compressed into the volume of a city, to have gravity so strong that potential energy is measured in solar lifetimes, to have a magnetic field so intense that rearranging it produces matter from nothing. The millimeter is not the cause in the way that a match is the cause of a fire. The millimeter is the release, the small mechanical permission that allows everything that was already stored, already wound tight, already waiting in the geometry of the crust and the topology of the field, to find its way out. The coin in your hand is still a coin. It is still 1 to 3 millimeters thick. Nothing about the physics described in this chapter changes what it is in your palm, what it weighs, how it catches light, but the millimeter is never quite the same unit again. Strike a metal bowl, not a plastic one, metal, the kind with some mass to it, the kind that was made by someone who understood that thickness affects tone. Strike it once cleanly and then take your hand away and listen. The sound doesn't stop when the impact stops. It continues, cycling through the air in the room, diminishing but present, carrying in its frequency something specific to the geometry and composition of that particular object. A thinner bowl rings higher. A larger one rings lower. Two bowls that look identical but were cast from slightly different alloys will ring differently, and a person with a trained ear can hear the difference without being able to explain precisely what they're hearing. The sound contains information. The vibration encodes the object. This is more or less what happens to a neutron star after a starquake. Less poetically, or actually no, the same amount of poetically, because the physics is doing something genuinely analogous and not just metaphorically adjacent to it. The fracture sends shear waves through the crust. Those waves reflect off the boundaries of the crust, the surface above, the crust core interface below, and they interfere with each other, and from that interference emerge standing waves, resonant modes, the star vibrating at specific frequencies that are determined by the geometry, composition, and internal structure of the crust itself. The star rings, physically, measurably in frequencies that encode its interior the way the bowl's tone encodes its alloy. These are called quasi-periodic oscillations, QPOs in the literature. Quasi-periodic because they are not perfectly regular. They drift slightly in frequency over the course of the burst, they fade and strengthen. They are not the clean sine wave of an idealized resonance, but something messier and more real. The way actual struck objects ring in the actual world rather than in textbook diagrams. The quasi is doing honest work. It is acknowledging that the star is not a perfect bell, that the medium it's ringing in is not a perfect acoustic space, that real physics produces approximations of idealized behavior rather than the behavior itself. But close enough. The frequencies observed in QPO data from magnetar giant flares span a wide range. The lowest detected cite around 18 to 28 Hz, well within the range of human hearing technically, though there is no air to carry them and no ear positioned to receive them. The highest observed reach into the kilohertz range. Between those extremes, In the tails of the largest flares ever recorded, multiple distinct frequencies appear simultaneously, the star apparently ringing in several modes at once the way a complex struck object produces overtones alongside its fundamental note. The 2004 flare from SGR 1806-20, which will get its own chapter because it demands one, produced QPO signals at frequencies including approximately 18, 26, 30, 92 and over 150 Hz, detected in the oscillating brightness of the burst's tail as the magnetar rotated and the ringing scar swept in and out of view. These numbers were pulled from the light curve of a burst that originated 50,000 light-years away, from an object 20 kilometers across, and they tell, in principle if the models are good enough, something about the thickness and composition of the crust, the strength of the magnetic field threading through it, the behavior of the superfluid in the layers below. In principle, the models are getting better. The field is not settled. Here is the personal opinion. QPOs are the part of this story I find most quietly astonishing. Not the energy numbers, those are staggering, but they arrive as data, as quantities to process. QPOs arrive as a different kind of information. They are the star talking about its own interior involuntarily through the specific way it vibrates after being broken. There is something almost uncomfortably intimate about that. The star has no intention of communicating. It simply vibrates at the frequencies its structure permits, and those frequencies, decoded from a light curve recorded on a satellite in Earth orbit, say something about what the inside of a neutron star is made of. The bell metaphor is useful here, but it has a limit, and the limit is worth naming before moving past it. A bell is a simple object with a simple geometry and a composition that doesn't change with depth. A neutron star crust is a layered structure with at least 3 or 4 distinct phases of matter stacked on top of each other, each with different density, rigidity and acoustic properties, floating on a superfluid that has its own oscillation modes, surrounding a core whose behavior is not fully known. The resonant modes of this object are not the clean overtone series of a struck metal surface. They are a complicated superposition of different wave types, shear modes in the solid crust, Alf-Venn modes in the magnetic field, torsional oscillations that involve the whole crust twisting slightly around the star's rotation axis, and disentangling which frequency corresponds to which mode and what each mode implies about which layer, is a problem that astrophysicists are still working through carefully. The bell rings. But reading what the bell is saying takes more than a good ear. Torsional oscillations deserve a moment, because they are the mode most directly connected to the crust's mechanical properties. A torsional oscillation is exactly what it sounds like, the crust twisting, one hemisphere rotating fractionally forward, while the other rotates fractionally back, oscillating around the equilibrium position. The frequency of this oscillation depends on the shear modulus of the crust, the rigidity, the resistance to this kind of twisting deformation, and on the mass distribution within the crust. Measure the frequency accurately enough, compare it to enough theoretical models, and you can begin to constrain what the shear modulus actually is, which constrains what the crust is actually made of, which constrains the equation of state of dense matter, which is one of the genuinely open questions in physics. A frequency extracted from the light curve of a distant explosion, telling us the composition of matter under conditions no laboratory can reproduce. It seems, and this is genuinely uncertain, which is the honest position, it seems like the QPO frequencies observed in the major magnetoflares are roughly consistent with torsional modes in a crust with the properties predicted by nuclear theory. Roughly. The match is not exact, and the disagreements are informative rather than fatal, pointing towards specific aspects of the models that need refinement. The superfluid in the inner crust complicates things considerably. It couples to the torsional modes in ways that shift the frequencies, and the degree of that coupling depends on poorly constrained parameters deep in the nuclear physics. So the star is ringing and the ring is informative, and the information is partial, and the partiality is exactly where the interesting work is being done. The ringing doesn't last. Minutes, in the case of the largest flares. Seconds or less for smaller events. The energy in the oscillations dissipates into the magnetosphere, into the surrounding radiation, into the interior of the star through the coupling between the crust and the superfluid below, and the frequencies fade. Not cleanly, not all at once, but gradually, the amplitude decreasing with each cycle, until the signal drops below the noise floor of whatever instrument was observing it. And then the star is quiet again. Quieter than before, actually. The fracture has relieved some of the crustal stress. The vortices that unpinned have dissipated some of the rotational lag. The magnetic field has settled into a new, slightly different configuration. The object that exists on the other side of the ringing is not quite the same object that existed before the fracture. It has adjusted, has released, has rearranged itself slightly in the direction of a new equilibrium. It will begin accumulating stress again almost immediately, because the physical processes that caused the fracture are still ongoing and will continue for as long as the star rotates and the superfluid exists inside it. But for a few minutes, the most energetic surface in the observable galaxy was vibrating at frequencies a human ear could theoretically detect, encoding its interior structure in the pattern of its light, ringing in the dark across 50,000 light-years. It does not know it was singing. The instruments that recorded it, though, those were pointed and waiting, and they heard something, and what they heard is still being carefully translated. There is a law in physics that does not negotiate. Angular momentum is conserved, not approximately, not in most cases, not under favourable conditions, conserved absolutely in any isolated system, regardless of what happens inside that system. Matter can rearrange, structures can fracture, layers can slip and shift and settle into new configurations, but the total angular momentum of the whole system, before and after those rearrangements, is identical. The law doesn't bend for neutron stars. It doesn't make exceptions for the most violent geological events in the universe. It simply holds, as it always holds, and everything else, including the spin rate of a dead star 20 kilometers across, has to adjust around it. When the crust shifts inward, the star's moment of inertia decreases. Moment of inertia is the rotational equivalent of mass, a measure of how much a spinning object resists changes to its spin rate, determined by both the total mass and how that mass is distributed relative to the rotation axis. Mass concentrated close to the axis produces a lower moment of inertia. Mass spread far from the axis produces a higher one. When a section of the neutron star's crust, which sits at the outer edge of the object, as far from the rotation axis as any part of the star gets, shifts fractionally inward, even by a millimeter, the distribution of mass changes. Not dramatically, not visibly, a fractional rearrangement of matter that was already at a relatively small radius in an object that isn't large to begin with. But the law doesn't care about fractions. If the moment of inertia decreases, and angular momentum must be conserved, then the rotation rate must increase. Has to. There is no other option the physics will allow. The spin-up is not a response to an external force, not a push from somewhere, not energy added to the system. It is a geometrical consequence of matter moving inward while a conservation law holds steady. The star spins faster because it has to, because the alternative would require angular momentum to go somewhere, and there is nowhere for it to go. The figure skater comparison exists for this. The arms pulled inward, the spin accelerating, and it is correct, technically the same physics operating at a radically different scale. But the comparison has a problem, which is that the figure skater is doing something intentional, is an agent choosing to rearrange herself, and the neutron star is not choosing anything. The crust fractured because it had no more capacity to hold its stress, and the spin-up followed because a conservation law required it to follow, and there is no agent and no intention anywhere in this sequence. Just physics producing consequences in the only directions it is allowed to produce them. Set the figure skater down. She's done her work. The spin-up happens fast. Whether instantaneous is the right word, actually, no, it isn't quite. Nothing in physics is truly instantaneous, but the time scale is short enough that the distinction barely matters observationally. The mechanical disturbance crosses the crust in milliseconds. The vortex unpinning and angular momentum transfer from the superfluid to the crust happens over seconds to minutes. The observable spin-up, at the precision of most current timing measurements, appears to happen essentially all at once, a step function in the rotation rate, a discontinuity in what had been, until that moment, a smooth and predictable curve of deceleration. The change in rotation rate is small. This is important to hold. The glitch, and this is where the word finally has to be used. The glitch is a fractional change in spin rate of somewhere between 10 to the negative 10 and 10 to the negative 6, depending on the event. The larger end of that range, 10 to the negative 6, means the pulsar's rotation rate increased by 1 part in a million. The smaller events are 1,000 times subtler than that. In absolute terms, for a pulsar spinning a few times per second, this corresponds to a speed up of perhaps a few hundredths of a microsecond per rotation. The pulse that had been arriving at a particular interval now arrives slightly early, not by seconds, not by milliseconds, by microseconds or less. And this is what I find genuinely hard to sit with about pulsar timing, that this is detectable, that humans built instruments sensitive enough to notice a clock running fast by a fraction of a microsecond from tens of thousands of light years away. The precision required to do this is not engineering precision in the ordinary sense. It is something closer to an obsession made physical, radio telescopes with timing pipelines that track pulse arrival times to nanosecond precision over baselines of years and decades, building a record of a rotating object's behavior so detailed that a 1 part in a million deviation in its spin rate appears in the data as an unmistakable discontinuity. The Vela pulsar has been glitching like this for as long as it has been observed. Its glitches are among the largest known, fractional spin-ups in the range of 10 to the negative 6, occurring roughly every few years, with a post-glitch relaxation that takes weeks to months as the superfluid couples back to the crust and the system settles toward its new equilibrium. The crab pulsar glitches more often but more gently, smaller events, more frequent, a different statistical signature that may reflect a different balance between the starquake mechanism and the vortex avalanche mechanism, or may reflect something about the relative youth of the crab compared to Vela. The most prolific glitching pulsar currently known, J0537-6910 in the Large Magellanic Cloud, has produced over 40 glitches in roughly 13 years of observation. Nearly one every 4 months, each one a small structural event inside a neutron star, each one announcing itself through a fractional deviation in a timing record, each one telling the instruments something about a crust and a superfluid that no probe will ever visit. Glitch. It is a genuinely bad word for this. A glitch is what a television does when the signal drops for a frame. A glitch is a minor software hiccup, a brief and inconsequential deviation that fixes itself. The word was borrowed into astrophysics from colloquial usage sometime in the late 1960s, when the first pulsar timing anomalies were being documented, and it has stayed because scientific terminology tends toward inertia once established. But calling what happens inside a neutron star during a starquake a glitch is— the mild irony of this deserves a moment. It is roughly equivalent to calling the eruption of a supervolcano a hiccup. The pulse arrives early, the data point sits fractionally off the trend line. A researcher somewhere, reviewing the timing residuals from the previous observation run, notices the deviation. That deviation is the only notification the universe sends. Something structural happened inside an object 50,000 light-years away. A crust fractured. A superfluid released its stored angular momentum. A dead star reorganized itself slightly, in a direction demanded by physics, on a timescale shorter than a human heartbeat. And the record of that event is a single data point sitting slightly above a line on a plot, in a file, on a computer, in an observatory, on a planet that the event never knew existed. The pulse keeps coming after the glitch, slightly faster, then gradually slowing again, as the star resumes its long deceleration, as the superfluid begins to recouple, as the crust absorbs the new equilibrium and begins again the slow accumulation of stress that will eventually, somewhere ahead in time, produce another deviation in another timing record. The clock runs slightly fast, then it corrects, and the star keeps going. The light left before humans had agriculture, before the first city, before writing, before pottery, before the domestication of anything, before any human hand had shaped a tool with the intention of leaving it for another human to find. The event that produced the light happened. The crust fractured, the magnetic field convulsed, the fireball expanded at a third of the speed of light, and the gamma rays departed, and the universe between the source and everything else was simply space, and the gamma rays crossed it at the only speed available to them. And the crossing took 50,000 years. 50,000 years of nothing. Of the light moving through interstellar gas and dust, through the plane of the Milky Way, across the far side of the galaxy, and then toward this side, toward this unremarkable spiral arm, toward this average star with its small system of planets, none of which knew the light was coming, none of which had any mechanism for knowing, because the universe does not send advance notice of what it is about to do to your ionosphere. On December 27, 2004, it arrived. It was a Tuesday, ordinary in every respect except the one that matters here. The light from SGR 1806-20, a magnetar in the constellation Sagittarius, approximately 50,000 light-years distant, making it almost exactly on the opposite side of the Milky Way from Earth, entered the solar system at the speed of light, crossed the distance to Earth in approximately 8 minutes from the orbit of Jupiter, and struck the upper atmosphere. What happened next was recorded by more than a dozen spacecraft simultaneously. The Rossi X-ray Timing Explorer, NASA's swift satellite which had launched just weeks earlier, and whose instruments were immediately and completely saturated. The RESI spacecraft, the International Gamma Ray Astrophysics Laboratory, Integral, which had been designed to observe exactly this kind of high-energy event and which nevertheless found its detectors overwhelmed in the first fraction of a second. Mars Odyssey, in orbit around Mars, recorded the burst. Cassini, then in transit towards Saturn, recorded it. The Ulysses spacecraft operating in deep space recorded it. Messenger, en route to Mercury, all of them simultaneously registering the same event from different positions in the solar system, their timing data later used to triangulate the precise location of the source in the sky. It is worth pausing on that list. Not because the number of spacecraft is impressive, though it is, but because the list includes probes scattered across the inner solar system and beyond, different planets, different orbital positions, different orientations, and all of them saw the same thing at the same time, within the light travel time corrections between their positions. The burst was not directional in any narrow sense. It was a sphere of gamma radiation expanding outward from SGR 1806-20, and by the time it reached the solar system, that sphere was 50,000 light-years in radius, and the entire solar system was a negligible point inside it. The initial spike lasted less than a second. In that fraction of a second, 200 milliseconds roughly, the energy released was equivalent to what our Sun radiates in 250,000 years. This number has appeared in this script before in a different context, but here it belongs to a specific event on a specific morning, not to an abstraction. 250,000 years of solar output in 0.2 of a second from an object 50,000 light-years away. The instruments didn't saturate because they were poorly designed. They saturated because the brightness exceeded the dynamic range of detectors built to observe the most energetic phenomena in the known universe. Nothing in the design specifications had fully accounted for this. After the spike came a tail. For more than 5 minutes, 6 minutes and 30 seconds by some measurements, which is an extraordinary duration for an event of this type, the burst continued, oscillating in brightness with a period of 7.56 seconds. That period is the rotation rate of SGR 1806-20. As the magnetar spun, the raging scar of the fracture swept in and out of the line of sight, producing the oscillation, turning what could have been a featureless exponential decay into a structured, readable signal. The star was, in a sense, labeling the event with its own rotation period. Every 7.56 seconds, a pulse for 6.5 minutes. The effect on Earth was not theoretical. The upper atmosphere, the ionosphere specifically, the layer between roughly 60 and 1,000 kilometers altitude where solar radiation normally ionizes atoms during the day and allows them to recombine at night, was ionized by the burst. On the night side of Earth, where it was dark and the ionosphere was in its recombined low conductivity state, the gamma rays from SGR 1806-20 ionized it back to a daytime state, instantly. The ionosphere on the night side of the planet behaved for the duration of the burst as if the sun had suddenly appeared. Radio communications were disrupted. Some low-frequency navigation signals were temporarily lost. The ionosphere expanded slightly and then contracted as the ionization increased and then receded, and that expansion and contraction was measurable, and it was measured. And fishermen in the Arctic, this is the detail that arrives and refuses to leave, that I keep returning to because it is the most human data point in this entire event. Fishermen in the Arctic on an ordinary December morning saw an unexpected aurora. Not a planned aurora, not one forecast or anticipated, just a sudden brightening in the sky because the gamma rays from a dead star 50,000 light-years away had ionized enough atmosphere to produce visible light, and the people closest to the polar regions, who happened to be outside and looking up, saw it. They didn't know what they were seeing. There was no reason they would have. The event also, according to some analyses, slightly and permanently shifted Earth's magnetic field. Not enough to affect a compass, not enough to matter to anything biological, but measurable, a small, real, permanent adjustment in the magnetic field of a planet, produced by a burst of electromagnetic radiation from a source 50,000 light-years away. The Earth was physically altered, incrementally, by a crack in the crust of a star that fractured before modern humans existed. SGR 1806-20 itself is worth holding in the mind for a moment. It has a magnetic field exceeding 10 to the 15th Gauss, the strongest magnetic field ever measured on any object. Earth's magnetic field is roughly half a Gauss. The magnetar's field is a quadrillion times stronger. It is the most highly magnetized object currently known to exist, and it sits 50,000 light-years away, which is, in the context of what it did to Earth's ionosphere from that distance, a deeply uncomfortable fact to linger on. A similar event, comparable energy release occurring within 10 light-years of Earth, would be sufficient to destroy the ozone layer. Not damage, destroy. The ultraviolet radiation reaching the surface afterward would be biologically catastrophic on timescales relevant to evolution. The closest known magnetar is approximately 13,000 light-years away. This is considered a safe distance. The question of whether a nearby magnetar starquake caused one of the known mass extinctions in Earth's history is not a settled question. It has been raised in the literature, examined, found plausible in mechanism but unconfirmed in evidence. The specific extinctions have specific leading hypotheses: volcanism, impacts, anoxia, and a magnetar hasn't displaced those. But the question isn't dismissed either. It sits in the plausible category, which is a category that deserves at least a moment's acknowledgement when discussing what a magnetar can do to a planet from 50,000 light-years away. What was produced at the source, at the fracture site in the magnetosphere of SGR 1806-20, was a fireball. The magnetosphere surrounding the star became a hot plasma of electrons and positrons, expanding outward at roughly 30% the speed of light. Behind the initial gamma-ray spike, which moved at the full speed of light, came this slower fireball, detectable in radio wavelengths as it expanded and swept up the surrounding interstellar medium. Radio telescopes tracked it for months afterward. The expansion rate, measured over time, allowed estimates of the total energy in the fireball, which in turn constrained models of the magnetic field strength and the geometry of the crust fracture that initiated it. In terms of gamma rays, the burst had an absolute magnitude of approximately -29. For context, the brightest star in the Earth's night sky, Sirius, has an apparent magnitude of about -1.5, SGR 1806-2. Had it been located at the same distance as Sirius, would have been roughly as bright as the full moon. Not in visible light, which human eyes could see, but in gamma rays, which human eyes cannot, and which would have sterilized the surface of the Earth. The event lasted 6.5 minutes. The light had been travelling for 50,000 years. By any measure available to human experience, the relationship between the duration and the journey is absurd. The burst was the largest event of its type ever recorded, 100 times more energetic than any previously observed soft gamma repeater flare. It was, on December 27, 2004, the brightest event originating outside the solar system ever detected in the history of human astronomy, and it came from something the size of a city. That morning, most of the world was 2 days out from Christmas. People were in the particular post-holiday drift that settles over the northern winter, unremarkable, going about the ordinary texture of a late December day. The ionosphere flickered. Some navigation signals dropped briefly. Fishermen in the Arctic looked up. The star that caused it had fractured 42,000 years before anyone on Earth had a name for stars. The first pulsar was not discovered. It was noticed. There is a difference, and the difference matters here. Discovery implies intention, a search with a specific target, a hypothesis confirmed, a thing found because someone went looking for it. What happened in the summer of 1967 at the Mullard Radio Astronomy Observatory in Cambridge was something quieter and stranger than that. Jocelyn Bell, then a graduate student, was working through paper chart recordings from a radio telescope she had helped build, looking for the signatures of quasars, when she found something that wasn't a quasar, a repeating signal, precise and regular, arriving from a fixed point in the sky. Her initial annotation on the chart was LGM1, little green men, not a serious hypothesis, a placeholder for something that didn't fit any existing category. It fit eventually. After other examples were found, after the regularity was confirmed, after the implications of that regularity were worked through, the object was identified as a rotating neutron star, and the field of pulsar astronomy began in earnest. But the first few months involved data sitting in notebooks and chart rolls, being looked at by people who did not yet have the framework to understand what they were looking at. The signal was real, the meaning was absent. This is how almost everything in pulsar timing history begins. The first glitch was found the same way, retrospectively, in data that had already been collected by people who went back to look at something that had seemed like noise or instrument error, and turned out to be the interior of a neutron star announcing a structural event. The Vela pulsar glitched in 1969. The Crab pulsar glitched the same year in September, a spin-up detected in timing data from multiple observatories. The researchers who found it, Radhakrishnan and Manchester, working independently on Vela, Richards and Comella on the Crab, recognized the deviation as real, as non-instrumental, as something the star had done rather than something the equipment had done. But what the star had done was not immediately obvious. The word glitch entered the literature around this time, borrowed from colloquial usage applied to a deviation in a timing record that was inconveniently difficult to explain. The word carried no physical model. It named the anomaly without proposing a mechanism. For a few years, the glitch was a description. The spin-up happened, the relaxation followed, the pulsar returned to something close to its previous behavior. Why this sequence occurred was an open question with several competing answers. The Starquake model arrived almost immediately. Ruderman proposed it in 1969, in a brief paper in Nature that runs to barely more than a page, suggesting that the spin-up could be explained by a sudden decrease in the star's moment of inertia, caused by a fracture in the solid crust relieving accumulated stress. The math was simple and the prediction was clean. A rigid crust building stress as the star slowed, eventually fracturing, contracting slightly, spinning up in response. The model fit the observations well enough to be taken seriously. It also fit too well, in a way that eventually became its own problem. The Vela pulsar glitch is too large for the Starquake model alone. The energy stored in the crust, the elastic strain that accumulates between events, the moment of inertia change that a crustal fracture can produce, when these are calculated carefully, the numbers come up short. The glitches Vela produces are bigger than a pure Starquake can account for. Something else is contributing angular momentum. The superfluid interior, the vortex unpinning mechanism that appears throughout this script, was added to the model to make up the difference, and the modern understanding of pulsar glitches is a hybrid, the Starquake as trigger or companion event, the superfluid as the angular momentum reservoir that does most of the heavy lifting. But this understanding took decades to assemble. The data was accumulating the whole time. There is a particular feeling, and this is the personal opinion this chapter has been holding back, in finding out that something was broadcasting a message for years before anyone could read it. Not nostalgia exactly. Something closer to the feeling of reading an old letter and suddenly understanding a sentence that made no sense at the time. The Vela pulsar was glitching before the concept of a glitch existed as a physical category. It was announcing its interior structure, the superfluid, the crust, the rotational lag, in every spin-up event, in every slow post-glitch relaxation, in every deviation from the trendline. The signal was there, the language wasn't. The radio telescopes were not hearing, of course. The thought should be corrected. They were recording. Electromagnetic pulses arriving at a dish, converted to electrical signals, written to magnetic tape or paper chart filed. The meaning was in the filing cabinet, waiting for the framework that would make it readable. When that framework arrived, and slowly, through competing models and refined measurements and improved theoretical understanding of neutron star interiors, the filing cabinets opened and the history inside them became legible. This is roughly how astrophysics has always worked. The universe transmits continuously. The receiving end develops understanding incrementally. There is always a gap between the signal and its meaning, sometimes years, sometimes decades, sometimes longer. Something worth saying here. This project is entirely self-funded. No sponsors, no network, just people who find this worth supporting. At 3,000 members, we move to full human voiceovers, a different kind of listening experience, built by the community that makes it possible. If that's something you'd like to be part of, the link is in the description. The sky is still speaking. The pulsars currently being monitored by timing arrays around the world, parks in Australia, the Lovell telescope in the UK, the 500-metre FAST telescope in China, the combined baselines of the International Pulsar Timing Array, are broadcasting their rotation rates with a precision that captures events at the microsecond level, building timing records that will eventually span decades. Every glitch that occurs in that dataset will be noticed, analysed, added to the growing catalogue. The catalogue currently contains several hundred glitches across dozens of pulsars. The distribution of glitch sizes, the waiting times between events, the post-glitch relaxation timescales, all of it is data, all of it constrains models, all of it says something about the interiors of objects that cannot be visited or imaged or sampled directly. The language is better now, not complete but better. The filing cabinets are open, the sky keeps transmitting. The shockwave doesn't stop at the crust. This is the thing that gets lost when starquakes are described primarily as surface events, as crustal fractures, as lattice failures, as geometric rearrangements of the rigid outer shell. The fracture happens in the crust, yes. The energy release is concentrated at the crust. But a shockwave propagating through material at a significant fraction of the speed of sound doesn't politely halt at a boundary, just because the boundary marks the edge of the region we understand well. It continues inward, into the star, into the layers below the solid crust, into matter whose behaviour is, and this word is being used carefully here, not for effect, genuinely unknown. Press a hand flat against a wall, feel the resistance. The wall gives no information about what's on the other side, not the temperature, not the texture, not whether the room beyond is empty or full. The resistance is complete. The surface is informative about itself and silent about everything behind it. This is roughly the epistemic situation with the neutron star interior below the inner crust. The surface of the object broadcasts its rotation, its magnetic field, its X-ray emission, and from these signals a great deal about the outer layers can be inferred. But below a certain depth, the signals stop carrying reliable information about what they passed through, and the theories that describe the matter at those densities have not been confirmed by any experiment that can currently be performed. The inner crust gives way to the core at a density of roughly half the nuclear saturation density, the density found at the center of ordinary atomic nuclei, the densest ordinary matter that exists in laboratory conditions on Earth. Below that transition, the matter is denser than anything a terrestrial experiment has ever produced, and the theoretical frameworks that describe it are extrapolations from physics confirmed at lower densities, extended into territory where their reliability is unknown. This is not a minor caveat. The core of a neutron star comprises roughly 90% of its total volume. What lives there, what the shockwave from a starquake propagates into, is the dominant constituent of the object, and it is not understood. Several possibilities exist, and they're not all equivalent in their strangeness. The most conservative possibility is a core of pure neutron fluid, dense beyond nuclear saturation, but still composed of the same neutrons that populate the inner crust, just more closely packed, behaving as a superfluid at the relevant temperatures. This scenario is tidy. It extends the physics of the inner crust inward without introducing new particle types or new phases of matter. The problem with it, or not exactly a problem, more like a tension, is that at the densities found at the center of a massive neutron star, the Fermi energy of the neutrons becomes high enough that it may be energetically favorable for them to convert into other particles. And if that happens, the core is not a pure neutron fluid. Hyperons are the first alternative. Particles containing strange quarks, lambda particles, sigma particles, Shawi particles, which are produced in high-energy collisions in particle accelerators, where they survive for fractions of a microsecond before decaying. In the neutron star core, the decay products of a hyperon would themselves need to undergo energetically costly transitions to form, and so the hyperons may be stable, pinned in place by the thermodynamic conditions, unable to decay because the environment won't permit the decay products. Strange particles made permanent by pressure and density. The problem with hyperons, and this is one of the genuinely contested questions in the field called the hyperon puzzle, which is a better name than most puzzles get, is that they soften the equation of state. Their presence makes the matter more compressible, reduces the maximum mass a neutron star can reach before collapsing into a black hole. And observations of neutron stars with masses around 2 solar masses have constrained the equation of state in ways that make a purely hyperonic core difficult to accommodate. The numbers don't quite work. Either hyperons are suppressed by some mechanism not fully understood, or the equation of state involves something else that stiffens the matter back up, or the 2 solar mass measurements are telling us something more subtle about the interior. The literature on this does not converge. It continues. Deeper still, toward the center of a massive neutron star, the densities may be high enough that the concept of individual nucleons becomes approximate. Protons and neutrons are not fundamental particles. They are composite objects, each containing 3 quarks bound together by the strong force. Under sufficient compression, the boundary between neighboring nucleons may become ambiguous, the quarks no longer clearly belonging to one particle or another, the binding becoming a collective property of the dense medium rather than a property of individual objects. This is quark matter, a phase of dense matter in which quarks move through a shared medium, rather than being confined within discrete hadrons. Quark matter has never been produced in a laboratory at 0 temperature. The relativistic heavy ion collider at Brookhaven and the Large Hadron Collider at CERN produce quark-gluon plasma, a hot, high-energy state where quarks are briefly deconfined. But this is a temperature-driven deconfinement, not the density-driven deconfinement that might exist in a neutron star core. The cold dense quark matter that theoretical models predict at neutron star core densities has no experimental analogue. The predictions exist. The confirmation doesn't. There is a further possibility, stranger than hyperons and only marginally less speculative than cold quark matter, called a color-flavor locked phase. A state in which quarks of different colors and flavors pair up in a specific highly symmetric arrangement, producing a material that is simultaneously a superfluid and a superconductor that break certain symmetries of the strong force in ways that produce unusual acoustic and transport properties. Whether this phase exists in neutron star cores is unknown. Whether it would produce distinctive signatures in the glitch behavior or the QPO spectrum that could be identified observationally as being worked out. The papers are being written. The question is open. Into all of this, the hyperonic maybe, the quark matter perhaps, the color flavor lock possibility, the shockwave from a starquake propagates. What it does when it arrives depends on what it finds. If the core is a pure neutron superfluid, the shockwave couples to the superfluid's oscillation modes and produces a particular pattern of vortex response. If hyperons are present, they affect the viscosity and the coupling timescales in ways that change how quickly the angular momentum transfer between interior and crust proceeds, and this in principle shows up in the post-glitch relaxation timescale, which is something that can be measured. If quark matter is present in the core, the acoustic properties are different, the coupling is different, and the glitch behavior may carry a signature of the exotic phase even if no direct image of the core is possible. This is the quiet, persistent argument in the literature. Which of the observable glitch properties, the spin-up timescale, the relaxation duration, the ratio of the spin-up magnitude to the long-term spin-down rate, can be used to discriminate between interior models? Which measurements constrain which phases? Where the data is already sufficient to rule something out and where more timing precision is needed? The shockwave goes inward. It encounters matter in a state that may have no name yet. It disturbs that matter. The disturbance propagates back outward in ways that depend on what was disturbed. The crust responds. The pulse timing records the response. Somewhere in that chain, from the fracture at the surface to the timing anomaly recorded by a telescope on Earth, is information about the deep interior of a neutron star. The chain is long and the decoding is difficult, and the models are not yet good enough to read everything the data contains. But the data is there. The shockwave went inward. Something responded. What it was is still being argued about, carefully in papers that arrive in the astrophysics preprint archive with the quiet regularity of people who are not sure what they'll find but are going to keep looking anyway. The gamma rays leave first. They always leave first because they are light. Because light is the fastest thing the universe permits, and because the fracture that produced them has no way of holding them. They depart the magnetosphere of the star at the speed of light, 300,000 kilometers per second, moving outward in a sphere that expands at that speed in every direction simultaneously, carrying the energy of the magnetic field's rearrangement encoded in their frequency and intensity. Within 1 second of the fracture, the leading edge of the gamma-ray sphere has expanded to a radius of 300,000 kilometers, which is roughly the distance from Earth to the Moon. Within 1 minute, it has expanded to 18 million kilometers. Within 1 hour, past the orbit of Venus. By the time it reaches the nearest star system, it is 4 years old and has expanded to a sphere 4 light-years in radius. Its energy diluted by the square of the distance, but still, for the most energetic events, measurable by a sufficiently sensitive detector. By the time it reaches the far side of the galaxy, if the magnetar is on this side, which some are and some are not, it has been travelling for tens of thousands of years, and the sphere is tens of thousands of light-years across. Behind the gamma rays, moving slower, comes the fireball. The fireball is matter. Electrons and positrons born from the energy of the rearranged magnetic field, produced directly from electromagnetic energy in a process called pair production. The physics that says a sufficiently energetic photon moving through a sufficiently strong magnetic field can convert spontaneously into an electron and a positron, matter and antimatter, both, from nothing but light and field. The fireball expands at a significant fraction of the speed of light. The 2004 event from SGR 1806-20 produced a fireball moving at roughly 30% the speed of light, tracked by the radio telescopes as it expanded and swept up the surrounding interstellar medium over the following weeks and months. The expansion rate, measured as a function of time, carried information about the total energy of the event and the density of the medium the fireball was moving through. The fireball doesn't reach Earth. It disperses long before that distance, diluting into the interstellar medium, thermalizing, losing its identity as distinct expanding structure. What reaches Earth from distant magnetar events is only the light, the gamma rays, the X-rays, the radio emission from the expanding shock front. The matter stays local, cosmically speaking. And then there are gravitational waves. The starquake involves a sudden redistribution of mass in a rapidly rotating object. A section of the crust shifts, the moment of inertia changes, the oblateness changes. In general relativity, any changing quadrupole moment in a mass distribution, any asymmetric redistribution of mass that changes shape over time, produces gravitational waves, ripples in the space-time metric propagating outward at the speed of light. The calculation is not in dispute. A neutron star starquake produces gravitational waves. Whether those waves are detectable is a different question, and the honest answer is, not yet. The amplitude of gravitational waves from a single starquake, estimated from the crustal displacement and mass involved, falls below the current sensitivity threshold of LIGO and Virgo for all but the most extreme hypothetical events and the most optimistic assumptions about the fracture geometry. The waves are there, in the sense that the physics requires them to be there, that the calculation produces a real number rather than zero. But the number is small enough that it sits below the noise floor of instruments that can already detect the gravitational wave signal from two neutron stars merging 100 megaparsecs away. Starquake gravitational waves are quieter than that, more localized, less total energy, shorter duration. Future detectors, the Einstein telescope, the proposed cosmic explorer, will be more sensitive by orders of magnitude. Whether their increased sensitivity will bring individual starquake gravitational waves into detectability range is being calculated. The papers are not conclusive, but the direction is clear. If the instruments get sensitive enough, the space-time ripples from a neutron star crust fracturing somewhere in the galaxy may eventually be readable. And if they are readable, they will carry information about the interior of the star that no electromagnetic signal can provide, because gravitational waves pass through everything without absorption, without scattering, without the filtering that electromagnetic radiation undergoes as it moves through matter. The electromagnetic signals tell us about the surface and the near magnetosphere. The gravitational waves, if they can be detected, would tell us about the mass distribution deep inside, different information, complementary, not redundant. Set gravitational waves aside for now. They are coming, in the sense that the physics requires their existence, but they are not yet in hand. The signal that has arrived and that has produced one of the more quietly startling scientific revisions of the past decade is the fast radio burst. A fast radio burst is a millisecond duration flash of radio energy, bright enough to be detected across cosmological distances, across hundreds of millions, sometimes billions of light years, arriving from a fixed point in the sky, lasting between a fraction of a millisecond and a few milliseconds, releasing in that brief duration as much energy as the sun emits over days or weeks. The first was detected in archival data from the Parkes Radio Telescope in Australia in 2007, identified by Duncan Lorimer and his student David Narkovic in observations that had been made in 2001. The signal sitting in the data files for 6 years before anyone found it. There is the delayed message feeling again. The signal arrived in 2001. It was found in 2007. It was not understood for years after that. fast radio bursts were mysterious for a long time, not in the casual way that word is sometimes applied to anything unfamiliar, but genuinely structurally mysterious, in the sense that their brightness temperature exceeded what any known coherent emission mechanism could straightforwardly produce, and their dispersion measures placed them at cosmological distances that seemed incompatible with a source compact enough to produce a millisecond pulse. The universe doesn't easily make things that are simultaneously very far away, and very brief and very bright in radio wavelengths. The combination constrained the possible sources severely. The constraint pointed toward neutron stars, specifically toward magnetars. The connection was confirmed, or rather strongly supported, in April 2020, when SGR-J 1935 plus 2154, a magnetar in our own galaxy about 30,000 light-years away, produced a radio burst bright enough and brief enough to qualify as a fast radio burst. It was detected simultaneously by the CHIME telescope in Canada and the STAR 2 detector in the United States. It was the first time an FRB-like signal had been definitively associated with a known magnetar, and it changed the conversation about what fast radio bursts are and where they come from. The current hypothesis, well supported but not proven for all FRBs because the population may not be homogeneous, is that at least some fast radio bursts are produced by starquakes on magnetars at cosmological distances. The crust fractures, the magnetic field rearranges. The magnetosphere is disturbed in a way that produces coherent radio emission. The specific mechanism is still being debated, with models involving charged bunches accelerated along field lines, or current sheets forming and reconnecting in the outer magnetosphere, or shock waves propagating through the magnetosphere and producing massive emission. The details differ between models. The basic picture is consistent. If this is correct, and the evidence is accumulating in this direction, then fast radio bursts have been arriving at Earth for as long as radio telescopes have been operating, and for most of that time, no one knew they were receiving signals from starquakes on dead stars billions of light-years away. The first confirmed detection of an extragalactic FRB was in 2007. The first detection of any FRB in archival data was of a signal from 2001. Before that, the signals may have been arriving and missing the detectors, arriving and being discarded as radio frequency interference, or arriving and simply not being noticed. Signals from crustal fractures, arriving unreceived, sitting in noise, this is the farthest consequence, a crack in the crust of a magnetar billions of light-years away, propagating outward as a sphere of radio energy that crosses the observable universe and arrives at a radio telescope on a planet that took years to recognize what it was hearing. The fracture that caused it happened before Earth formed, possibly before the solar system existed, in a galaxy so distant that the light travel time is a significant fraction of the age of the universe. And it arrived, and it was recorded, and it is slowly being understood. The crust broke somewhere out there a very long time ago. We are still receiving the news. The pulse comes back, not immediately, in the seconds after the fracture, in the minutes while the magnetosphere is still reorganizing itself around the new field geometry. The radio emission may be disrupted, the beam temporarily altered, the clock briefly irregular in ways that go beyond the simple spin-up. But within minutes to hours, depending on the event, the pulse returns. The radio beam sweeps the sky again. The timing record resumes. And what the timing record shows, in the days and weeks following a large glitch, is not a return to the previous behavior. It is something more complicated and more interesting than that. The spin-up happened in milliseconds. The relaxation takes much longer. Weeks, sometimes months, sometimes, for components of the recovery that involve the deepest coupling between the superfluid and the crust, potentially years. The post-glitch timing record shows the rotation rate declining from the elevated post-fracture value back towards something close to the pre-glitch spin-down trend. But the approach is not clean and not linear. There are components that relax quickly and components that relax slowly, and the mixture of timescales in the recovery curve carries information about which parts of the interior are involved in the event and how strongly they are coupled to the observable crust. The quick component, the part that relaxes over hours to days, reflects the recoupling of the parts of the superfluid most directly connected to the crust, the vortices in the inner crust that unpinned and transferred their angular momentum and are now repinning, re-establishing their connection with the lattice, the differential rotation between superfluid and crust decreasing as they synchronize. This part of the recovery is relatively well understood, in the sense that the models produce timescales consistent with what is observed, in the sense that the physics of vortex repinning and mutual friction is tractable enough to calculate. The slow component is less settled. There are neutron stars, Vela is the clearest example, having been monitored for long enough that the post-glitch behavior is well characterized, where the timing record shows a residual, a persistent offset from the pre-glitch trend that doesn't fully relax, even over months. The star doesn't quite return to where it would have been if the glitch hadn't happened. The spin-down rate after the glitch is slightly different from the spin-down rate before it. The trajectory has changed, and this persistent change, this refusal of the post-glitch state to converge exactly on the pre-glitch extrapolation, is one of the signatures of what the starquake did permanently as opposed to transiently. The magnetic poles have moved, not dramatically, not by degrees, not by any amount that would be visible in the pulse profile to casual inspection. But the starquake, in pushing matter fractionally toward the magnetic poles as the crust rearranged, altered the alignment between the star's spin axis and its magnetic axis. The magnetic braking torque, the mechanism by which the star loses angular momentum to electromagnetic radiation, depends on this alignment. Change the alignment even slightly, and the spin-down rate changes. The new spin-down rate is permanent because the new pole positions are permanent because the new crust geometry is permanent. This is the thing that the word recovery gets wrong, and the correction is worth making slowly rather than quickly. Recovery implies return, a disrupted system restoring its previous configuration, a clock that ran fast for a moment returning to its correct rate. The neutron star does not do this. The neutron star settles into a new configuration that is in some ways similar to the old one, still spinning, still emitting, still following the long, slow deceleration driven by electromagnetic radiation, but is structurally distinct from it. The crust has a new geometry. The poles are in new positions. The superfluid, having released a fraction of its stored angular momentum, has a new distribution of vortex density. The star that exists 3 months after the glitch is not the star that existed 3 months before it. They are the same object in the sense that a room is the same room after furniture has been moved. The walls are the same, the floor is the same, but the arrangement is different. And if you knew the previous arrangement well enough, you would notice. The timing residuals settle. Not to zero, there's almost always a small persistent offset, but to something close enough to a smooth trend that the event begins to recede into the record as a data point rather than an active disturbance. The telescopes continue monitoring. The arrival times continue being recorded. The post-glitch residuals become part of the baseline from which the next glitch will be measured. Because there will be a next glitch. The physical processes that cause the fracture have not stopped. The crust is still cooling, still being stressed by the ongoing mismatch between its frozen oblateness and the equilibrium shape demanded by the current spin rate. The superfluid is still rotating slightly faster than the crust, still accumulating lag, still loading its vortices against their pinning sites. The relief provided by the starquake was partial, a fraction of the stored stress released, the lattice settling into a slightly less strained configuration. The vortex density redistributed but not eliminated. The system is calmer than it was before the fracture, but it is not at rest. It begins again. The accumulation that took centuries to build the stress for the previous glitch begins rebuilding from a new baseline. The new crust geometry is stiffer in some places, more vulnerable in others. The magnetic field, now in a slightly different configuration, evolves under its own slow decay and continues to stress the crust in new directions. Everything that was true before the glitch remains true after it, operating on the same timescales, building toward the same kind of threshold, with slightly different initial conditions. Months after the glitch, the timing record looks almost ordinary. A pulsar spinning down gradually, its pulse arriving with the precise regularity that makes these objects useful as natural clocks. The event that disrupted that regularity has receded into the data archive labelled, time-stamped fitted with a model. The post-glitch residuals have relaxed. The spin-down rate has stabilised at its new value. The star is not recovered. The star has adjusted. There is a difference, and the difference is the whole point of this chapter, and it is also, if it is honest, a difference that applies more broadly than to neutron stars. Systems that experience structural events do not return to their prior configurations. They find new equilibria that resemble the old ones in function, that perform the same basic behaviours, that look from a sufficient distance like nothing much has changed. But the interior arrangement is different. The geometry has shifted. The trajectory forward from the new configuration is not the same trajectory that would have proceeded from the old one. The pulse comes back. The clock runs again. It is not the same clock. Right now, while you're reading this, a radio telescope somewhere is pointed at a pulsar. Not metaphorically right now, actually right now, tonight, at this hour. The Parkes telescope in New South Wales, a dish 64 metres across sitting in a shallow bowl of Australian hills, cycles through its monitoring program across the night sky. The FAST telescope in Guizhou province in China, 500 metres across, the largest filled aperture radio telescope ever built, a structure so large that it required the relocation of the village that previously occupied the site, observes pulsars with a sensitivity that makes everything built before it look approximate. The Lovell telescope in Cheshire, the telescopes of the European Pulsar Timing Array, the instruments of the North American Nanohertz Observatory for Gravitational Waves, all of them in their respective observing windows, collecting pulses from rotating neutron stars and recording the arrival times to nanosecond precision. The pulse is arriving, right now, the timing pipeline is running. What the astronomers who built these systems are waiting for is a deviation, a pulse that arrives fractionally early, a step function in the rotation rate, the signature of a crust that has fractured somewhere in the galaxy, while the instruments were pointed at it, the news travelling to Earth at the speed of light, arriving as a single data point sitting slightly off the trendline. This is what years of observation are listening for, in addition to the gravitational wave science and the interstellar medium studies and the tests of general relativity that pulsar timing also enables. Somewhere in the data, at some unknown moment, a glitch will register. They cannot predict when. This is not a temporary limitation, not the kind of not yet that implies a solution is being worked toward. The starquake is a threshold event in a complex system. The stress accumulates, yes, and the threshold exists, Yes, but the precise moment at which a specific lattice site fails and triggers the cascade is not deterministic in any practically useful sense. The accumulation can be estimated from the spin-down rate. The expected glitch size can be roughly inferred from the statistics of previous glitches in that pulsar's history. The waiting time between events can be modelled probabilistically. None of this adds up to a prediction. It adds up to a probability distribution, and probability distributions don't tell you when. They tell you something about the space of possible whens, and then they wait alongside you. There are pulsars in the current monitoring catalogues that have glitched many times. Vela J0537-6910, a handful of others with rich glitch histories stretching back decades. And there are pulsars that have never been observed to glitch despite years of observation, and there are pulsars that glitched once and then went quiet. The variety of glitch behavior across the pulsar population is itself a dataset, constraining models of what determines glitch size and recurrence, telling something about the range of interior configurations that neutron stars can have. But even for the most reliably glitching pulsars, the next event is not scheduled. The crust is accumulating stress on its own timeline, indifferent to the monitoring program. The vigil is not watching in the way that watching usually works. It is not directed attention waiting for a visible event, not the kind of watching that a person does when they are waiting for something they can see coming. It is, and this is the one soft comparison this chapter will allow itself, more like the way a seismograph waits, not anticipating a specific earthquake, not sensing the build-up, just running continuously, recording everything, available to capture whatever arrives in the stream of data, the event indistinguishable from non-event until the analysis identifies the deviation. The seismograph doesn't know it's waiting. The radio telescope doesn't know it's waiting. The patience belongs to the scientists who built the systems and maintain them and process the data on schedules that continue regardless of whether anything interesting happens on any given night. There is something about this, about the maintenance of attention across years and decades for events that cannot be predicted, that feels worth sitting with for a moment, at this hour, in whatever room you're in right now, the particular quality of late-night consciousness, when the house is quiet and the world outside has settled, and your own thoughts are doing something slower and less directed than they were a few hours ago. That quality of attention, still present, still receiving, but softened at the edges, is something like what these monitoring programs do, spread across years instead of hours, the instruments running through the night in a dozen observatories while the astronomers who design them sleep and wake and go about their lives. The pulse keeps arriving, milliseconds, seconds, years of accumulated arrival times, each one a data point in a record that will eventually be long enough to reveal things about the interior of the star that no current model can extract from shorter baselines. The value of pulsar timing is partly in the individual measurements and partly in the accumulation. The decades of data that reveal slow drifts, subtle changes in spin-down rate, the faint signatures of events that would be invisible in any single observation but become legible in the long record. This project is self-funded. No sponsors, no network support, just people who find this worth keeping alive. If that's you, Patreon is where it happens. We are genuinely grateful for every person who makes this possible. And there are people whose ongoing support deserves to be named. Alison, who has been here since the very beginning, and whose steadiness has meant more than she probably knows. Matthew M. and Brian Winter, whose support and presence are woven into everything this project has been able to do, and to everyone else on Patreon, thank you. Quietly, genuinely, without ceremony. This exists because you decided it should. The crust of the Vela pulsar right now is under load. Not dramatically. The glitch history of Vela suggests events occurring roughly every few years, and the last one provides a rough starting point for the accumulation, though the starting conditions after a glitch are not identical to the conditions after the previous one. The superfluid is accumulating rotational lag. The lattice is absorbing shape stress. The vortices are pinned and loaded. The threshold is somewhere ahead, at a distance that cannot be precisely measured, on a timeline that cannot be predicted. This is happening tonight. Not as a metaphor for uncertainty, or a poetic frame for the limits of knowledge, as a physical fact occurring right now in an object about 1,000 light-years away, broadcasting its rotation rate to any instrument sensitive enough to receive it. The pulse is arriving. The data is being recorded. Somewhere in a future timing residual, the glitch is waiting to be found. The crust doesn't know the telescopes are listening. The telescopes don't know when the crust will break. And somewhere between those two facts, in the space between an indifferent star and a patient instrument, across 1,000 light-years of galaxy, something is being measured that has no name more precise than attention. The pulse comes again, and the night continues, the way nights do, without announcement, without conclusion, moving at its own pace toward a morning that will arrive whether or not anything in the data changed.